formula of impedance. That was whatever it is, XL minus XC or XC minus XL whole square plus R square under. Okay, then cos phi and tan phi are also important because one of the questions we saw where the phase angle was also asked. Okay, so this is it. And then yes, we discussed the resonance condition. In resonance, I told you the XL means the inductive capacity, the inductive reactance, and the capacitive reactance. These become exactly equal. So when they become equal, then we have the current maximum because the net resistance decreases. And impedance becomes equal to
Z is equal to R.
R. Becomes equal to R. Omega is equal to 1 by under root LC, and linear frequency is 1 by 2 pi into 1 by root LC. Okay, we practiced questions, then we saw this quality factor. What was quality factor is it basically told us the sharpness of resonance, and to increase the quality factor you have to have the minimum value of the resistance, very low resistance. Now, when we're talking about a quality factors formula, we said the ratio of the resonant frequency to the bandwidth. And what is the bandwidth? Difference between the frequencies on both sides of the graph of the resonant frequency. Here, the current becomes 1 by root 2 of the current at the resonance condition. So from here, we got the formula of the quality factor. That was 1 by R under root L by C. We stopped it. Okay, any doubts still here? Should I proceed further?
No doubt. Yes,
Okay.
ma'am.
All right. See, this question says in series LCR circuit, the resonant frequency is 800 hertz. So this is the resonant frequency given to us. Omega R is given to us as 800 hertz. The half power points means those 2 points that we take on either side of the graph. These
Yes,
are
ma'am.
those. Okay, so half power points can also be written. So half power points are, this is first frequency. Omega 1 is 745 hertz. And second one, omega 2 is 855 hertz. It says you have to calculate the Q factor of the circuit and the bandwidth of the circuit. For the bandwidth, if I calculate the bandwidth first, it would be easier. Tell me, what is the formula of bandwidth?
W1 minus W2.
Yeah, means higher minus lower. So W2 minus.
W2 minus W1.
Because frequency won't be negative. So whatever is it, adjust it accordingly, one or two. So this becomes 855 minus 745. So this is how much? 110 hertz?
Yes, ma'am.
Okay. Now talking about the Q factor. Now it's better to calculate the Q factor. So can I write Q factor as omega R divided by omega 2 minus 1? Is it right?
Yeah.
Okay.
Yes,
So
ma'am.
now what I'll do, omega R, this is 800 divided by this is 110. So around 7.7 something it will come, no? 11 into 7 is 77. So 7 point something it will come. Okay, approximately around 7.2 it will come. This much will be the quality factor. Now it has no ratio because the frequencies get cancelled. Hertz from here and hertz from here, they get cancelled. Okay. So write down this question.
Ma'am, I'm done.
Okay. But earlier, no, there were these LR circuit and RC circuit also used to come. Means, see, what have we studied? We have studied three individual resistors and capacitors and inductive circuits separately. That's what we did. That is there.
Yes, ma'am.
Okay, and after that, you have the series LCR circuit also in your syllabus. That's there. Okay. In fact, LCR circuit is the most important topic, one of the most important topic of this chapter. This resonance and quality factor, they combine together. I think one question I gave you in the last class, which had all these things.
Yes, ma'am.
So yeah. So see, and one thing, you're not writing the units in the assignment. You will lose on marks for the units. I'm telling you, whether it's your physics or chemistry, in both of these units have to be mentioned. Okay, so write the units in physics and chemistry. Both of these subjects marks will be cut if units are not mentioned. There are chances, right? You don't know who is going to check your paper. So I think in your assignment everywhere I've written units, and the remark also I've sent as the unit. Did you see the paper? Right.
Yes, ma'am.
Right now you submitted the induction one. No, AC's assignments are left.
Yes, ma'am. One more assignment is left.
But
I
from
think it was the
EMI.
last. Yeah.
Okay.
No, I don't know. It was the last one. I don't really remember which one it was.
Okay, just check and share if it is from EMI. At least your EMI part should be done so that now you can focus on alternating current also. And just as I told you before, only revise EMI chapter so that in the
Okay, ma'am.
test. Yeah, so I was saying, so these things are there in your syllabus. Earlier, we used to have these individual circuits and a lot of theory about them. Now, they have not been clearly said that these two circuits are cut. So there are chances they can give you these two circuits, but you just have to know about the basics of them. So I'll also just tell the basics just in case if you find these questions still in the board exams, because it's not very clearly mentioned in the syllabus or anywhere. Usually the things that are mentioned, they mention it in the CBSE syllabus, but these two topics aren't mentioned this time. But it has also not come that these topics are one of the deleted topics. So just practice it. It's very easy though, I'll just tell you. So keep this thing in mind, okay? So revise it
Okay,
at
ma'am.
the end. Revise these topics more. Now, series LR circuit means two we'll do LR and RC. LR means resistor and inductor, these two are only connected. So it becomes very easy. See, for resistors, individual part, current and voltage, they are in the same phase. For inductor, we know voltage leads the current by pi by 2. Okay. Now there is no capacitor present. So wherever in the whole LCR part, wherever we were getting C for capacitor or XC, that won't be there. Just make it 0 in that whole thing. You will get the answer for LR circuit because XC is not there. Now see, if I draw the phasor diagram, it would be just this. I don't have to decide whether it's VL minus VC or where will the final resultant point out. So I'll just have the resistor voltage across the resistor like this and the voltage across the inductor is like this. That's it. Okay, that's it what is required and that's it what I've put. This is how we'll have the phasor. Coming to the impedance triangle, you will have the resistance, you will just have the VL, you will have Z. You won't have VL minus VC this time. So when we take out the Pythagoras theorem, E naught square means this hypotenuse square is equal to perpendicular square plus base square. This is the perpendicular, this is the base. Same, I hope you remember we did the same thing. It was just VL minus VC whole square here. Same derivation we have done using an impedance triangle. So E naught square is equal to I naught square R. Now see, VR is equal to I naught into R. I have written as voltage is equal to current into resistance. So VR is equal to I naught into R. Plus VL, this is current into again the resistance. So for inductive circuit, we just have XL as our resistance. So I naught into XL whole square. So E naught square is equal to I naught square R square plus XL square. Okay. Now,
Okay, ma'am.
current will be EMF divided by the resistance. Same impedance formula we'll get under root R square plus XL square. Instead of XL minus XC, you are just getting XL square. Like in the main formula, if you put XC as 0, you will just get XL square only. So this is it. Okay. Same derivations. You
Okay.
have cos phi, and cos phi won't change anywhere in any of the calculations, but tan phi will be different. Tan phi was XL minus XC by R, VL minus VC by VR. Here it will just be XL by XR or VL by VR. Okay. So this
Okay,
is
ma'am.
the circuit. We'll practice one question based on this. You copy down this first. Okay.
Ma'am. Can you scroll down? Ma'am, can you scroll down? Ma'am, can you scroll down? None, ma'am.
Okay, let's see one numerical based on this. See, this is a resistor connected, this is an inductor connected. So this clearly tells us that this is an LR circuit. Now
Mm.
it says calculate the impedance of the circuit and the phase angle between voltage and current. So what's the formula of impedance?
Z is equal to R square plus XL square.
R square plus XL square, correct? Under root, yes?
Uh,
Okay. So what's the
Yes, ma'am.
resistance?
90. No,
Is
wait,
it?
no. We have to calculate the resistance. V is equal to IR.
Okay, V is equal to IR. Voltage is 90.
Yeah.
Current is 3. Resistance. This is equal to 30 ohms.
Yes, ma'am.
Okay. And what about this is VR, right? And we got the value of R then. Next.
And then we have to calculate for inductor also.
How?
V is equal to IR. We have to calculate the resistance. So
VL is equal to IR.
IXL.
IX. So this is equal to how much it is given? 120. This is given as 120. Current is 3 into XL. So XL is equal to 40 ohm.
Yes, ma'am.
So we have the resistance now. We have the inductor. Impedance is equal to, this is equal to 30 square plus 40 square under root. So Z is equal to 50 ohm. That's the impedance of the circuit.
Yes, ma'am.
Okay. Talking about the phase angle, you can use any value. Cos phi, you can use cos phi is R by Z. You can use tan phi also, that will be XL divided by R. You can use any value.
Mm.
So resistance was 30 by 50. So phase angle is basically cos inverse 3 by
Please answer.
5. So that's the angle. Mostly the angles will be in such a value that you'll not be able to calculate them. Okay.
Mm.
Write down the solution, then one more circuit we'll do and we'll move on to power and energy.
Okay, ma'am. I'm done.
Okay. See, now talking about the RC circuit. RC circuit means resistor is there and a capacitor is connected. So in resistance, we've already talked about that the current and the voltage, they'll be in the same phase. While in the capacitance, current will lead this time than voltage by pi by 2. So here, see, now in the LCR circuits formula, wherever XL was coming, that will be 0 this time. Okay.
Mm.
So see, now when we draw the phasor diagram, the resistance is ahead, the VR is ahead, and that's how we draw, means the part of the voltage across the inductor that will be missing here. So VC is there. Now you take the impedance triangle, same thing when you plot E naught square is equal to VR square plus VC square. So E naught square is equal to VR can be written as I naught into R whole square plus VC can be written as I naught into XC. So E naught square is equal to I naught square R square plus I naught square XC square. So from here I naught square is taken out. I naught square is equal to E naught square divided by R square plus XC square. You bring this term to the Ohm's law. That is equivalent to the resistance. That makes it the impedance of the circuit. So under root R square plus XC square this time, tan phi will be VC by VR, okay, or XC by R. That's it. Just write it. Now we'll move on to the next topic, power and energy. Is this clear? RC and LR just in
Yes,
case.
ma'am. Ma'am, cos phi will also work, right?
What? Yes, cos phi will be
Ma'am,
the
cos
same.
phi will work.
Will be the same.
Okay.
Cos phi will not change. Cos phi will be R by Z. Okay.
Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am.
Okay. See now power and energy of the AC circuit, because we've already talked about the power of the normal DC circuit. So we discussed power is equal to voltage into current, remember?
Yes, ma'am.
When we discussed the heating effect of electric current, that time I discussed with you power is VI, and what is the formula of heat?
Heat is,
H is
ma'am, I
equal
don't
to
know.
I square RT.
Yeah.
So see here now the formula of the EMF is E naught sine omega t, and current is I naught sine omega t minus phi, or you can take it in either ways. Wherever you want to situate this phi, your answer will be the same. Like I just assume that, let's say the current is lagging by some phase angle phi. Okay, you can take it here also. You can lag the EMF or the current, whatever. Okay, because see, you are going to just use an identity which will make everything even. So just put anything, and see E naught I naught here, sine omega t minus phi will be there. Now, what do I do in order to use and apply an identity? Because here's this is not an identity. This cannot be solved further. So if I multiply and divide it by 2, okay. So 2 sine A sine B I'll get. 2 into sine A, this part will act as A. This will act as A and this will act as B. So 2 sine A sine B is equal to cos A minus B minus cos A plus B. I'll show you that. 2 sine A sine B is equal to cos A minus B. Your A and B are not phi and omega t. Okay, they are not phi and omega t. This omega t is your A and omega t minus phi is your B. Okay.
Yes, ma'am.
So if I open up the brackets here, see, power is equal to, this becomes E naught I naught divided by 2. Now, cos A minus B. A, subtract this, minus omega t plus phi, because minus sign will change the sign. Did you get this? Omega t minus omega t plus phi? Okay, minus. Now, cos A plus B. That is omega t plus omega t minus phi. Yes. From here, omega t gets cancelled, so you are only left with cos phi. And this makes it cos 2 omega t minus phi. This equation.
Yes,
Okay.
ma'am.
Now cos 2 omega t minus phi is 0. When we calculate, it is 0. So see, what's the average power that we'll get ultimately after this whole derivation? Second cosine term, why is this zero? The reason for this is that whenever you calculate the average power, the second cosine term over an average cycle, or when you calculate the average value for a full cycle, it will be zero. Okay, so if you want, you can use the brackets like this, cos 2 omega t, to show the average. For average, we write these brackets in maths. Do you know? So like this also you can use for these, and that will be zero. Now coming back to what we are left with. We are left with E naught I naught divided by 2 cos phi. Yes. Now see,
Yes, ma'am.
if I want this 2, can I write this 2 as root 2 into root 2? It's the
Yes,
same
ma'am.
thing. So this will make power as E naught I naught cos phi divided by root 2 root 2. That's it.
Yes, ma'am.
Now, can you tell me what exactly is this E naught by root 2?
ERMS.
Yes, and I naught by root 2?
RMS.
Very good. Perfect. So power is equal to ERMS IRMS cos phi. This is the formula. You can use any of it. If you have to write it in terms of the peak value, you can use E naught I naught by 2 cos phi. That is also valid. Okay, so P is equal to ERMS IRMS cos phi. Depending upon the values of cos phi, you'll have to put it. Okay, so ERMS
Okay, ma'am.
IRMS cos. So this I hope I no not have to write. I'll just mark it. This is the power. ERMS is what? ERMS is RMS value of E, and this is RMS value of current, while this is the phase angle. Okay, I hope you know these terms.
Yes, ma'am.
Oh. Now for purely resistive or okay, we'll discuss this later. You write it till here, then let me discuss it. Okay.
Okay, ma'am. Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am, can you scroll down? Done, ma'am.
Okay. When we talk about the power, this is a power's general formula for any circuit, any AC circuit, alternating current circuit. Okay. Now, if you have a purely resistive circuit, can you just tell me what's the formula of phi that we get? What's the value of phi that we take in resistive circuit?
5/2?
Purely resistive circuit. What's the angle between current and EMF?
No, no, it's 0. No, yeah, 0.
Zero. They are in the same phase. This is the phase
Yes,
angle.
ma'am.
Okay, 0 degree.
Yeah.
So power is equal to ERMS IRMS cos 0 degree. Yes. Now cos 0 degree is
1.
1. So power here will be the maximum. ERMS IRMS. That's it. Okay, this is the maximum value of the power that is possible. This is the maximum value. Okay. Now see, for purely capacitive and inductive circuit, tell me.
It's 90.
90 degree, because one leads or one lags by 90 degree. So this is 90 degrees. So when I write the formula of power, ERMS, IRMS cos 90 degree. What is cos 90?
0.
0. So power will be 0. Okay, the minimum value of power you will get, that will be 0. Okay.
Okay,
Now,
ma'am.
there's a concept of wattless current. Wattless current basically means that when the average power is 0, if your average power is 0, in that case, you get the alternating current is termed as the wattless current. Okay, so where the power 0? In which circuit?
Resistive circuit.
In
Ma'am, the resistive circuit.
here we got it as 0.
No. Oh, okay. Yeah, I thought the power of it. So
No, no,
purely
no.
capacitive. Sorry.
Capacitive and inductive. No, it's clearly written. What kind of
And
answer?
capacitive.
Okay. So see, the alternating current which is obtained in average power through AC circuit is 0. Means this condition, when you have this condition for these two circuits, then you get a wattless current. The current is termed as a wattless current. Okay. So in that case, now you know power is 0 means cos phi is equal to 90 degree. Okay. That's it. What you have to do. Now, this is one thing. Wattless current has come in the board exams. Okay, this is from your previous year current, previous year questions. Now, when we talk about the power factor is nothing but this cos phi that we have been studying for so long. R by Z. So you will say, what is power factor? It's the ratio of resistance to the impedance. Okay, but it's the angle. So cosine only will give. So whatever cos, what you have been studying this, yes, we have already been studying about the cos phi. So same cos phi, it's just termed as the power factor, because many questions have said this, calculate the power factor of the circuit. So you just have to calculate cos phi. Now, whatever it takes to calculate cos phi using the data that is given in the question, utilize it and then calculate. Okay.
Okay, ma'am.
Okay, this I'll tell you later. You first write.
Ma'am, can you scroll down? Ma'am, I'm done.
Okay. See, when we have the average power no, over a capacitor or inductor, sometimes it gets, the question is to prove that average power is zero over a cycle. Okay. So you can use inductor, you can use capacitor. Any for inductor's energy, the formula is half Li square. For capacitor, it is half CV square. Now, you can prove for any. I have done it for capacitor. You start with the inductor. The difference will come that EMF will be leading by pi by 2. That's it. As I said, see, ultimately costs and sign are common in both of them, and you will use identity and everything will become exactly the same. So E is equal to E naught sine omega t. I is equal to I naught sine omega t plus pi by 2. Now, sine 90 plus theta is cos theta.
Yes, ma'am.
Now, work done is equal to power into change in time. Yes, if I use the equation of dw, this is power into dt. Now, the formula of power from here is equal to E naught into I. E into I basically. Power is equal to E into I. So, power is equal to E naught sine omega t and I naught cos omega t. Now, if I take dw, I'll have to multiply this whole power thing with time. So that will give me
Yes, ma'am.
dw is equal to, with this dt here, E naught sine omega t, I naught sine omega t dt. Now, for a full cycle, we are proving that the power, average power is zero. This is not for a half cycle, okay? And the device that I've used is a capacitor. So see, now putting the full powers value, E naught is there, I naught is there. Okay. Sine omega t, cos omega t is there. So if I multiply and divide it by 2, the same equation, if I multiply and divide it by 2. So I'll get 2 in the denominator and 2 sine theta cos theta is equal to sine 2 theta. So I can say E naught I naught by 2 is sine 2 omega t dt. Now I'll have to integrate it from 0 to 2. So E naught I naught will be taken out. Now instead of sine 2 omega t dt is left. All right. And what is this? This is power. See, power is equal to work done divided by time. So this was the equation of work done. So if I divide it by time, I'll get the power formula. Now see here we just have to put in the values. Power average, this is E naught, I naught by 2t. Here when you integrate it, what will you get? Tell me.
Sine 2 omega
What?
t. Wait, no, sine becomes cos. Minus, not minus, cos. 2
Minus cos.
omega.
Minus cos.
So yeah, omega t minus 0.
Omega t.
T
Okay.
minus cos 2 omega.
No, no, no. See,
Remember, this is 0, right?
see, sine 2 omega t becomes minus your whatever it is, no? Sine constant theta, whatever it is. Let's say constant theta. When you integrate it, it becomes minus cos this constant theta, but you divide it by this k, whatever was the constant. So here you will divide it by 2 omega. Yes.
Yes,
And then
sir.
we will put the limit from 0 to t in the next step. That's how we integrate. First, we write
Yeah,
the integral,
I
then we put. So
understood.
don't put the limit directly, otherwise you'll forget. You'll just put it in sign. Okay. Now see,
Okay.
average power will be E naught is there, I naught is there, by 2t is there. Now we are going to put in the limit. You take minus sign here only. Now see, cos 2 omega capital T minus cos 0 degree. Yes. And this
Yes,
whole
ma'am.
thing is getting divided by 2 omega. Okay. Now cos 2 omega t, you already know this is 0, right? So this whole term will,
Yes.
this whole term as I discussed with you, this is 0. So you get the average power as 0 itself. Okay. So sometimes it
Okay,
gets
ma'am.
to prove it. You start with inductor, you will land on the same derivation. So for inductor and capacitor, it comes to proof. Okay. Write it,
Okay,
then
ma'am.
we'll practice question and then we'll move on to transformers. That will be the last topic. Okay, please write it. I hope it's clear, Basmi. Any doubts you have till now?
Yeah. No,
Clear?
ma'am.
Okay.
Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am, can you scroll down? I'm done.
Okay, let's practice one numerical based on this. This says a light bulb is rated at 100 watt for a 220 volt supply. You have to find the peak voltage of the source, resistance of the bulb, and the RMS current through the bulb. See, 100 watt is the power given, and VRMS or ERMS is given as 220. Whatever is the supply voltage, no, Basmi, that becomes your ERMS. Now tell me
Okay,
peak
ma'am.
voltage, how should I calculate?
E naught is equal to ERMS into root 2.
Yes, very good. ERMS into 2. That makes it 220 root 2 volt. Solving part you can do later. Okay, now second says resistance of the bulb. See, from here, if you remember the formula that we have done, V square by R. In the DC circuit, this was
Yes,
for the
ma'am.
direct current. So for EMF, this becomes your ERMS square divided by R. So this is for, so R will be equal to P by E RMS square. So resistance will be P is, sorry, ERMS, I've written top. This is for AC. So from here, resistance will be ERMS square divided by the power. So ERMS square will be 220 into 220 into 2. Root 2 into root 2 will become 2 divided by 100. So that cancels it. This is 284 into 2.
Yes, ma'am. Yes, ma'am.
86568 ohm. Second part says RMS current through the bulb. Now RMS current is very easy once you know ERMS, you know resistance. Third part IRMS is equal to, see, V or E I have used, so I'll use E. ERMS divided by R. So this is equal to the ERMS is equal to IRMS into the resistance.
Yes, ma'am.
So from here, we can say IRMS is equal to ERMS divided by R. So IRMS will be, ERMS is 220.
220.
And resistance is around 568. So this much of ampere will be the answer. Okay.
Ma'am, ERMS is 220 root 2.
ERMS is
So,
not 220.
oh, okay, okay. No, I got confused. Yeah.
All right. Now there's a topic LC oscillations that's deleted from your CBSE syllabus. Okay. So we won't be doing it.
Okay.
Write it, then let's come to transformers. A little bit of theory we can see, then tomorrow we'll complete it. Okay.
Okay, ma'am. Ma'am, can you scroll down? Ma'am, can you scroll down? Done, ma'am.
See what's basically a transformer. It's a very, very small topic of this chapter. Transformer is a device that, see, when you have voltages, there are two kinds of voltages that are possible. A very low voltage, a very high voltage. So sometimes it's needed to get a high voltage from a low voltage, and sometimes it's required to reduce down the higher voltage to a lesser value. So transformer is what? Transformer basically is applied in alternating current to convert low voltage to high voltage or high voltage to low voltage. Okay. So let's say it is an electrical device for converting an alternating current because it's valid for AC only at low voltage to high voltage or vice versa, high to low. Now, if it converts the device from low to high, so low to high, just imagine as if you're moving upstairs, right? You're moving from the lower to the higher, you're going upstairs. So this kind of transformer, this is called as a step transformer. Okay, step
Okay, ma'am.
transformer. And it is the opposite, higher to low, it decreases the voltage. This is called a step down transformer. Okay, this is a step down transformer. All right, and the entire principle of the transformer is based on mutual induction. Okay, now there are two kinds of constructions that are possible. One type, one other is the shell type. So co-type, it's a hollow rectangular, concentric rectangular part where one side is tied to the primary wire turnings, another is tied to the secondary. See, mutual induction. Remember, we talked about the turnings of solenoid and we talked about the mutual induction. So similarly, here it is. So primary is this, secondary is this. And in shell type, basically, in one side, they are in very close proximity to each other. Here, they are not in close contact to each other in the core type. But okay, this distance is sufficient for mutual induction to occur. But in shell type, they are completely in contact with each other on the same rod. The primary turn has been wound up where the secondary turn is wound up. Okay. And basically, again, the same thing of mutual induction that we studied, change in this one causes the flux change in that and all. Okay. So this part will be clear when
Yes,
you
ma'am.
revise mutual induction and come. Okay. So just in after today's class, just revise mutual inductance, induction once. Okay. So same thing that we studied in the mutual induction. When the alternating current flows in the, see, we talked about the DC current in mutual induction. So that's why this is just the difference. Here also, when we talked about the primary circuit, magnetic field comes, magnetic field either increases or it decreases, or due to which the magnetic flux increases or decreases, which we say this is the change in the flux. Yes. So in the primary part, you have the change occurring, which leads to the change in the induction of the current or the EMF in the secondary coil. Okay, induced EMF will occur in your secondary coil. Okay, so that's how your primary wire is helping in the secondary wire. That's how we studied in mutual induction. Difference lies in the fact that there we were talking about the direct current, here we are talking about the alternating current. Okay, so what's the
Okay,
work?
ma'am.
As the alternating current flows through the primary, it generates alternating magnetic flux. Basically, in the primary one, when the current changes, magnetic field changes, magnetic flux changes. This is what is meant by it here, which passes through the secondary. Means when the flux is being changed in the first one, whether it's your core type or shell type, will induce a current in the secondary. So due to change in magnetic flux, change in magnetic flux in the primary, induced EMF will occur in the secondary. Okay. And self
Okay, ma'am.
EMF will be there in the primary coil as well. Remember when we talked about mutual induction, I talked about a coefficient of coupling as well. And I told you two wires, let's say these are two wires and they are mutually put like this. Okay. So because of both the wires are in close proximity with each other and mutual induction is possible, mutual induction will be there. But these individual wires will have their own self-inductances. So that is what
Yes,
is
ma'am.
self-induction will be there in the individual wires. Not of course in the second one because the flux is being changed in the first one. So in the primary coil, you will have the self-induction and mutual induction in both of them. Is it clear?
Okay, ma'am. Yes, ma'am.
This will be more clear when you revise mutual induction. So tomorrow you revise mutual induction and I'll discuss this again and then you can copy down also and we'll practice certain numericals from this. And tomorrow only
Okay, ma'am.
EM waves I'll start with you. Okay. All
Okay,
right.
ma'am.
I hope your vacations are still going on.
Yes, ma'am.
It's
There's
till
still 2
25th
more weeks.
August. Till 25th?
Yeah.
Okay,
Yes,
so
ma'am.
when your half yearly's exam will be there, right now you must have no update. When the school will reopen, then only will be. Okay.
Yes,
Just
ma'am.
just inform me, Basmi, okay? Because I want to